All right, so we're going to move on and start talking about flash processes, which is going to be one of the first applications we deal with here in class. So flash separations are probably the most straightforward vapor-liquid equilibrium based separation that we could think of. It's a good opportunity for us to get used to this idea of combining material and energy balances with equilibrium information. This is going to be something that we see throughout the rest of the course, and so we'll start here with flash processes. So your WANCAT textbook gives you a flow diagram of a typical flash distillation system. We're going to go through a few examples in class about how we do calculations related to this. But the general idea here is that we're going to feed a compressed liquid into a drum. I've got a picture of that here shown on the right-hand side. And essentially what happens is as we go into that drum, we're going to use a valve to basically throttle the mixture and drop the pressure. So this valve that's located here is going to cause a drop in pressure. And the way that we're going to set this process up is to drop that pressure such that at the given composition of the mixture, we're going to end up with a thermodynamic situation where we get phase separation into a vapor and a liquid. And in situations where we have a relative volatility that's greater than 1, and so we have a difference in volatility between the components, what we're going to see is a situation where the more volatile component is going to be preferentially separated into the vapor phase, and the heavier or less volatile component is going to be preferentially separated into the liquid phase. And then the drum is set up to take the vapor off the top and the liquid off the bottom. And so we get a separation of the components of our mixture just through this one flash process where we go through this phase separation process that uses the volatilities of the compounds to ultimately do a separation. And in class, we'll talk about two different limiting cases for this. We'll talk about one where we want to operate this process isothermally. In other words, whatever we're feeding into the process is going to be the same temperature as the drum temperature. And in order to do this, we're going to have to supply some heat to the system to keep the temperature constant. And in that particular case, we're going to see that we can do sequential mass and energy balances to help us with that process. Then we'll also consider a situation where we consider an adiabatic flash process, and in this case we're going to need to couple the mass and energy balances in order to do the analysis. We'll see how all that plays out during class, but here just wanted to introduce a few concepts that'll be useful for us as we get ready to work through some of those examples. So what we're going to do is we're going to think about the flash process in terms of a PXY diagram, right? We've talked a little bit about how we can use this visual representation of VLE information to be helpful to us. And so we're going to do that here for flash calculations. So because we're thinking about the flash process as one where we're going to drop the pressure, we'll use the PXY diagram to think about this. And so if we were to come in and draw an arbitrary PXY diagram, we might get something that looks a little bit like this. And I'm going to purposely draw this a little bit here to indicate there might be some non-ideality coming into the system. But ultimately, we could think about this in terms of how we would go through and do the thermodynamics calculations, whether we're using Raoult's law or whether we're using Aspen to go through and calculate our PXY diagram. We could generate the bubble and dew curves here for our analysis. And so we've got a situation where we have our two-phase region, and because of the way our process is set up, right, we're going to start with some pressurized liquids. So we might be starting somewhere up here, and we'll say that this particular pressure is going to be our feed pressure. And we're going to say that the composition of this feed is going to be Z1. So here we're using Z to indicate the feed composition. That'll be something that we have a tendency to do a little bit throughout the semester. And so one of the things that we need to be able to do is we need to be able to make sure that when we drop the pressure, that the drum pressure ends up somewhere in the two-phase region for this particular system at the composition of Z. And so if we were to extend this Z1 line down, right, we would see that there's some upper limit pressure. So we'll call that P upper. And there's some lower limit pressure. And in order to get a separation, we better have a drum pressure that's in between these two. And the drum pressure is just going to be whatever pressure we get to after we go through that valve that throttles the mixture. And so, we've got a range here that we could look at operating with, and we're going to see through some of our analysis that depending on the pressure we drop to, we're going to affect the compositions of the mixture, but we're also going to affect the amounts of the vapor and liquid that would come off of this particular drum. So we'll look for that as we work through some of our examples. I'll note here that at least for Raoult's law, we want to think about how we could go through and calculate this upper and lower pressure, right? So we know in this case we could think about doing bubble or dew pressure calculations based on our value of Z, and so I would encourage everybody to think about how, given the constant T situation of this PXY diagram, you could use the Z information and the T information along with Raoult's law to calculate the P upper and P lower values for this particular system. We'll leave that as an exercise for you to work on in your study groups, but that would be a good thing to think about. All right, so let's come back to our discussion here, and let's just assume and pick a somewhat arbitrary point here. Let's say we come in and we set our drum pressure to be equal to this value I'm sketching out right now. All right, so we'll extend this out and just label this. This is going to be P drum. All right, so we've taken our pressurized liquid feed, and through that valve we've dropped down in the pressure to P drum. And when we go through that phase separation, what we're going to get now is a situation where we have a vapor product and that's going to have some composition, call it Y1, but we'll read that off the horizontal axis as the composition of component 1 in our vapor process, or product. And we'll do the same thing over here for our liquid. And this we'll call X1. And so you can see here, as you change the pressure of the drum, you can affect the different compositions of component 1 in the liquid and vapor products. But again, as we mentioned, right, we've got this situation where we're also going to be in a situation where the lever rule tells us about how much of the vapor product or how much of the liquid product we get, and that also will change in a way that counteracts what's going on with the purity. As a general rule of thumb in these situations, if you make a more pure vapor product, you are likely to get less of it. But if you make a less pure vapor product, you can often get more of it. And we'll see how that plays out using the lever rule as we go. So we want to think about self-study in terms of the upper and lower pressure limits here, given the feed composition and the temperature. But this is what's going on in the flash drum. We're just dropping the pressure from a compressed liquid into the two-phase region. And as you see, we get a situation where, relative to Z, component 1, the more volatile component, is enriched in the vapor product, or Y1 is greater than Z1, and component 2 is enriched in the liquid product, or X1 is less than Z1. All right, so the other thing that we're going to need to take into account as we go through and think about flash processes is that we're going to need to do some things with energy balances. And so we want to refresh our memory here a little bit in terms of how we deal with energy balances and how we deal with particularly enthalpy. I'd encourage everybody to take a look at section 11.4 in Matsoukas. We're going to stick with the WANCAT nomenclature here, using the small h for the liquid phase enthalpy. Matsoukas uses the capital H for enthalpy. And WANCAT uses capital H to indicate the enthalpy of a vapor. So we're going to recognize that the H's here are all enthalpy, and we're going to have some nomenclature stuff to think about and sort out as we go. In any case, for an ideal solution, we can just sum up the mole fraction weighted enthalpy changes of the components in that solution, and that gives us our enthalpy change of the overall ideal solution. And so relatively straightforward. We don't have any non-ideal effects that would give us a delta H of mixing in this process, so we can just use the mole fraction weighted enthalpy changes of each of the components to get our value for the ideal solution. Now, oftentimes we work with a reference state, and I know this is something that you've discussed in 2215 in terms of doing these types of energy balances. But typically we can express these changes in enthalpy relative to some reference temperature. And so, given that we know that the definition of the constant pressure heat capacity is del H del T at constant pressure, right? We can take advantage of that and use that to adjust the enthalpy from one temperature to another. Remember, we generally expect that enthalpy is a very, very weak function of pressure, and so usually we're less concerned with that and more concerned about how enthalpy depends on temperature. So remember, we can do that, and oftentimes it's convenient to set the reference temperature such that the enthalpy at the reference temperature is equal to 0. And so if we do that, then that wipes out the H evaluated at the reference temperature. And this is one of the ways that we can sort of get out of having to talk about a change in enthalpy, because we can talk about what appears to be a fixed value or absolute value of enthalpy, but it's really relative to the 0 point that we've set based on the reference temperature. When we get into the HXY diagram in class, we'll talk a little bit more about seeing where that reference temperature is, and we'll see in the examples how this plays out. But just wanted to remind everybody that this is something that is commonly done and that we'll see as well in our examples. So with that, then we can think about, for our ideal solution, if we set that enthalpy at the reference temperature to be equal to 0, then we can express the ideal solution enthalpy as just the sum of the mole fraction weighted integrals of the constant pressure heat capacity of each component integrated over temperature from the reference temperature to T. And remember that these heat capacities can be complex functions of temperature, and so we need to factor that in. An example calculation that we'll think about for an ideal binary mixture that's being fed to a flash process is something that looks like this. Here we might be interested in calculating the enthalpy of the feed at some feed temperature and a composition Z1. And we would see that this enthalpy would be made up of two terms. We'd have the first term for component 1, where we'd have a heat capacity of the liquid for component 1. We'd integrate that from Tref to the feed temperature. We multiply that by Z1 and add that to Z2 times the comparable integral for the heat capacity of the liquid for component 2. And that would give us a way to figure out what the enthalpy of the feed is that's being fed to our flash process. Now, strictly speaking, all of these enthalpies are defined using integrals due to the definition of the constant pressure heat capacity. But in some cases, we have situations where either the heat capacity is not a particularly large function of temperature over the range of integration here, or it may be appropriate to take an average heat capacity. And that's another step that we can take in this process, or we can take the heat capacity of the liquid to be a constant or average value between TF and TREF. And depending on the circumstances, this might be something that works out well. It gets us out of having to do a more complex integral, but it either relies on the assumption of having a CP value that doesn't change much over the temperature range, or the ability to define an average value somewhere between the reference temperature and the feed temperature. And so those are two different ways that you can go about approaching this question of calculating the feed enthalpy. As we talk a little bit more about HXY diagrams and flash calculations, we're going to see how this comes in and how this helps us answer questions about temperatures or the amount of heat that we need to add to the flash process in order to, for example, maintain an isothermal flash process. And so we'll work through some examples of these during class, but wanted to give everybody a little bit of a primer and a little bit of review on some of these issues related to energy balances, because we're going to be working with these through those examples.